Now that we've learned how to write full electron configurations, we're going to focus on writing shorthand configurations and something called orbital notations. Let's focus on orbital notations first. So the rules for placing electrons in atomic orbitals, there are three of them. There's the off-bow principle, which means that electrons fill available orbitals from lowest energy to highest. In the ground state, all the electrons are in the lowest possible energy level. And so whenever we did our Hog Hotel, it means that the electrons have to enter in the first level before they move into the second level, before they move into the 2p, before they move into the 3s. So you have to go in order from lowest energy to highest energy. So this would be wrong because we would need to put electrons in the 1s before we move up to the 2s. Hund's rule says the electrons must be placed into the orbitals in such a way that no pairs are put together unless absolutely necessary. Single electrons would be placed into the boxes first before they are paired up if necessary. So in our Hog Hilton, in the 2p here, these were rooms on the same floor. The electrons, or the hogs, would go into the room or the orbital one at a time first as singles before they would pair up. So this is wrong because these two electrons would have one in this room and one in the next one before they would become paired together. The Pauli exclusion principle states that electrons come in two varieties based on the direction they're spinning. There is an upspin and a downspin. Up and down spins are always paired together, and up or down combinations are not allowed. No two electrons can ever be in the same place at the same time. So that means that in this 1s, I have two up arrows. That would violate the Pauli exclusion principle because if they're in the same space, they have to have opposite spins. So one up arrow, one down arrow to represent this. Rules for placing electrons in atomic orbitals. Remember the Hog Hilton. Electrons enter orbitals of lowest energy first. They have to have opposite spins when they are in the same orbital. And Hund's rule says if you're going to put electrons in a p or d or an f sublevel, then you're going to have to put them in one at a time, up arrows first, before you start pairing them up, down arrows second. So now let's learn how to write orbital notations for electrons. Electron configurations show the way electrons are arranged around the nucleus of an atom. A more detailed way of showing electron configurations is with orbital notation. You are able to tell which orbitals are filled and which are unfilled. Remember to follow Hund's rule. So if this is the full electron configuration for sodium, 1s2, 2s2, 2p6, 3s1, how would we write the orbital notation? First of all, when you have an s sublevel, it can only have one orbital. So we would write 1s, one blank to represent the orbital, and then you can have a max of two electrons in that orbital, one with an upspin, one with a downspin. So we would write 1s2. Next is 2s2. S can only have one orbital, and so we'll draw one blank to represent that orbital, two electrons, one upspin, one downspin, and a 2 here because we have two electrons in the orbital. Now the p sublevel can have three orbitals. So when we write 2p, we're going to give it 1, 2, 3 orbitals, and then we're going to have 6 electrons, but when we place electrons, we're going to do up, 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 and then come back and pair them off. Down, down, down. Up arrows first, down arrows second. That's going to be 6 total electrons in this entire sub-level. And then finally, the 3s can only have one orbital, and we have only one electron in that orbital, so it's just going to be placed with an up, and then we'll put a 1 here to denote that. This is an orbital notation. Now we're going to write the full electron configuration for sulfur. Here is sulfur. Notice we're going to have to start from the beginning of the periodic table and work our way all the way to sulfur. So across row 1, it goes 1s2. Now I'm going to go across row 2. This is 2s2. And then over here is 2p6. Now I'll go to row 3. From here to here, it's 3s2. And then I'll go across, and it's going to be 3p, 1, 2, 3, 4. Now we're going to write the orbital notation for sulfur. So first we have 1s2. So I'm going to write 1s. S orbitals, S sublevels can only have one orbital, and it has 2 electrons, one up spin, one down spin, and we'll put a 2 to denote that it's full. Next is the 2s2. So I'll write 2s. S sublevels only have one orbital, up arrow, down arrow, and a 2 to denote these 2 electrons. Now it's the 2p sublevel, and in a 2p sublevel we can have 3 orbitals. 1, 2, 3. We have 6 electrons, and they have to be placed up arrows first and then down arrows second. It's Hund's rule that they are single, single, single before they become pair, pair, pair. We have a total of 6 in this sublevel. Next is 3s2, and so we'll place 3s. S can have one sublevel, and we have 2 electrons in that sublevel, up spin, down spin, here's the 2. Finally, 3p4 and p sublevels have 3 orbitals, and then we only have 4 electrons, so we have to place them up arrows first, 1, 2, 3, and then my final 4th one is a down arrow in the first orbital. So we have single, 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 and then pair in the first orbital. So this is 4 electrons total there, and so this would be the orbital notation for sulfur. Now let's write the full electron configuration for potassium, which I have highlighted here. Notice it's on row 4. We're going to start from the beginning and work our way to potassium. So across row 1 is 1s2, 1s2. Across row 2, it's 2s2, 2p6, 2s2, 2p6. Across row 3, 3s2, 3p6, 3s2, 3p6. And now I'm on row 4. Notice that it's row 4. We are stopping in the S block, and it's the first column, so this is 4s1. Now let's write the orbital notation for potassium. So first, I'm going to take my 1s. S sublevels can have one orbital, which is denoted with a blank. We have 2 electrons, one up spin, one down spin, and we'll put a 2 there. Next is 2s2, so I'm going to write 2s2, one orbital, up arrow, down arrow for my 2 electrons. Next is 2p. The 2p sublevel has 1, 2, 3 orbitals. We have 6 electrons. They have to enter up, 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 and then down, down, down. And then 6 is the total in this sublevel. Next is 3s, and because it's an S sublevel, it has one orbital, 2 electrons, one up arrow, one down arrow, and there's my little 2. Now, 3p. Remember, p sublevels have 1, 2, 3 orbitals. 6 electrons, and they're going to go up, 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 and then down, down, down. 3p6. Singles before pairs. Finally, 4s1, we're going to put 4s. There's only one orbital for S sublevels, and there's only one electron in this one, so we're going to have an up arrow, and we're going to put a 1, and that's the orbital notation for potassium. Finally, we're going to do the full electron configuration for nickel. And here's nickel on row 4. So we're going to start from the beginning. Row number 1 is 1s2, 1s2. Row number 2, 2s2, 2p6, 2s2, 2p6. Row number 3, 3s2, 3p6. 3s2, 3p6. And then row 4, it goes 4s2. Let me write that. And then something happens when we get to the D block. It's the row number -1. So this is going to be 3D, 1, 2, 3, 4, 5, 6, 7, 8. So it's going to end on 3D8. Now let's write the orbital notation for nickel. For my 1s2, an S sublevel can have one orbital and a max of 2 electrons, 1s2. 2s2, S sublevels, All right, the 2s2 can have 1 orbital and a max of 2 electrons. Now I'll write 2p6. P sublevels can have 3 orbitals, and we're going to put our arrows up, 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 and then go back and put down, down, down. That is Hund's rule. 2p6, now 3s2. I'll write 3s2. S can only have 1 orbital and 2 electrons maximum up and down. Next is 3p6. So I'm going to draw 3p6. P sublevels have 1, 2, 3 orbitals. Electrons enter single, single, single before we get pair, pair, pair. And there are 6 electrons in that sublevel. Next is 4s2. 4s2. S sublevels have 1 orbital and then 2 electrons max, up arrow, down arrow. Finally, we have 3d8. And I'll write it here, and I'll try to squeeze it in. D sublevels have 1, 2, 3, 4, 5 orbitals. And when we put our electrons in these 5 orbitals, it's going to be up arrows first. So 1, 2, 3, 4, 5. We need 8. So we have 5, 6, 7, 8. So it's going to be pair, 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 and then we have single, single. We are following Hund's rule. Singles in orbitals first before you start pairing them off. And this is the orbital notation for nickel. An alternate way of showing orbitals is in this increasing energy vertical kind of manner, where you would place the electrons in the bottom energy level first, followed by the 2s, then the 2p's, then the 3s, then the 3p's, and so on. Which rules are being broken by the following orbital notations? So what is being violated in this first one? Well, 1s2, that looks fine. 2s, well, there's only 1 in the 2s, and then they moved on to 2p. So this is where the mistake is, because you have to finish filling the 2s before moving on to the 2p, and that is violating this principle right here, the off-bow principle. Next, 1s2 up and down looks good. 2s2 up and down looks good. 2p, there's 2 of them, but this is wrong because you should put a single here and then a single there before they pair up. They're going to not want to share a room too quickly, and that is violating Hund's rule. So what is the correct notation for carbon? We should have 1s, 1, 2, 2s2, and then 2p2, where there's a single in this first box and then a single in this second box to represent the total of 6 electrons that carbon has. Now we're going to look at shorthand for electron configurations, which are also known as noble gas configurations. So we're going to be using these guys, which are at the end of the periodic table. That last vertical column or family is known as the noble gases. And we're going to use them to represent part of the electron configuration. And then we're going to continue from the beginning of the next row and work our way to the element in which we are representing. So now let's look at some examples of how to do this. First, let's write the full electron configuration of magnesium. This is magnesium here. We want to go through row number 1, and so that's going to give us 1s2. Then we're going to go through row number 2. This is going to be 2s2. This is going to be 2p6. And now we're on row number 3, and we're going to stop here in the S block, so it's going to be 3s12. To write the shorthand configuration for magnesium, we're going to go up. See, it's on row 3. We're going to go up to row 2, all the way to the end, and we're going to find our noble gas, which is one of these elements in the last column. We want the noble gas from the previous row. So since magnesium is on row 3, we want the noble gas at the end of row 2. We're going to place that noble gas in brackets. And what that's going to represent is everything from rows 1 to 2. Then I want to finish my configuration by going from the beginning of row 3 and stopping at wherever my element is. In this case, it's 3s2. And so this is the shorthand notation for magnesium. So now let's write the full electron configuration for calcium, which is located here on row number 4. So we want to go through row number 1. That's going to give us 1s2. Then we're going to go to the beginning of row 2, 2s2, 2p6, 2s2, 2p6. Then we go to the beginning of row 3, that's 3s2, 3p6. And now we're at the beginning of row 4, and we're going to go from row 4 and we're going to stop at our element, which is calcium. So it's row 4, the S block, 1, 2. So we're going to end with 4s2. To write the shorthand notation for calcium, it's on row 4, so we're going to go up to row 3 all the way to the right. And we're going to find the noble gas at the end of row 3, which is argon. So we'll place argon in brackets, and that takes care of rows 1, 2, and 3. And now I'm going to go back to the beginning of row 4, and I'm just going to work my way to my element. In this case, would be 4s2. And that's the shorthand notation for calcium. For our last example, we'll go straight to the shorthand notation of nickel. And since nickel is on row 4, I want to go find the noble gas at the end of row 3, which is going to be argon. So I'm going to place argon in brackets. That's going to take care of rows 1, 2, and 3. And now I have to go back to the beginning of row 4 and work my way to my element. Here is 4s2. Remember that this is the D block here, and so the row number -1 is going to be our energy level. So this will be 3D, 1, 2, 3, 4, 5, 6, 7, 8. So that'll be 3D8 to complete our shorthand notation of nickel. There are some exceptions to the rule. The highlighted elements below are exceptions in which an S electron moves to the D sublevel to create a more stable configuration. For example, copper has a 4s2 3d9 configuration, but if one electron moves from the S over to the D, we get 4s1 3d10, which is considered more stable because half-filled orbitals and full orbitals are better than those that are off balance, more stable. So these 4 that have been highlighted on the periodic tables are the 4 exceptions that would have an S electron move to its D sublevel. So now let's identify the elements that have the following electron configuration or orbital configurations. So if we look for 4s2 on the periodic table, what do we land on? Well, it's row 4, it's in the S block, and it's in the second column. So this element is calcium. Next, if we look for 4d2, we're going to go to row 4, but in the D block. That's tricky because remember that these are actually the row number -1. So my 4d is actually on row 5. So it's going to go 4d, and I'll count 1, 2. And so this element is zirconium. Okay, 5f14. Remember, also tricky, these are the row number -2, and so this is 4f. And then when I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, we land on this element over here, which is ytterbium. Next, we're going to find, where is 5p1? Well, we're going to go to row 5, the P block, and we're only going to go 1 into the P block, so that's going to land us on indium. When we look at the orbital notation, the very last thing we see is this, 4p, 1, 2, 3, 4. So I would go to row 4, go to the P block, and count 1, 2, 3, 4 blocks in, and that lands us on selenium. So now you'll do some practice on Canvas.